All right, welcome to The Explainer. You know how sometimes you look at a mathematical proof on a page and sure, you get the logic, but you just can't see it? Well, today we're going to fix that. We're exploring this absolutely brilliant geometric puzzle from the 19th century, and we're bringing it to life, turning abstract math into something you can actually hold in your hands.
So let's dive right in. We're starting with a geometric puzzle. And on the surface, it seems pretty simple, but it actually hides a real challenge for our imagination, a big disconnect between a simple rule and a very weird definition.
Okay, so on one side we have a rule you probably remember from school. You slice a cylinder at an angle, and the edge of that slice, it creates a perfect ellipse. Simple enough. But then, on the other side, you've got the official, much stranger definition of what an ellipse is. It says that for any point on that curve, its combined distance to two special internal points, the foci, is always the same. It's constant.
So, here's the puzzle, right? How in the world does a simple slice of a cylinder magically follow this very specific, kind of bizarre rule about two focal points? I mean, the math on paper works out, we know that, but how can we actually see it? That's the huge leap of imagination that has stumped people for a very, very long time.
And that brings us to this total stroke of genius from the 19th century. A Belgian mathematician named Dandelin, great name by the way, came up with this incredibly elegant physical way to solve this very puzzle. Dandelin's idea starts with this really clever, beautiful instruction. Just imagine taking two spheres, each one perfectly sized to fit snugly right inside the cylinder. Now, you just slide them in from opposite ends until each one just kisses the surface of that angled slice.
And just like that, Dandelin gives us these physical anchors for what was a totally abstract proof. These two spheres nestled right up against the slice, they're the key. They unlock the entire mystery, and they're going to show us exactly where the magic happens.
Okay, now let's jump to a modern 3D model to see exactly how this whole thing works. We're going to deconstruct this proof piece by piece so you can really see it.
First up, we've got the chamber. So this model uses a cylinder that's been cut in half, just so we can see what's going on inside. And that angled shelf there, that represents the flat plane that's slicing right through it, creating our ellipse.
Next come the anchors. So, just like Dandelin told us to, these spheres are placed so they just touch that angled plane. And here is the first big aha moment. The exact points where those spheres touch the plane become the two foci of our ellipse. Suddenly, they're not some abstract math concept anymore. They are real physical locations. And finally, this is where it all comes together. See that green ring? That's the ellipse itself. The red and blue rods are measuring the distance from any point on that ellipse down to our two foci. Now, just watch what happens. As you trace a point around that green ring, the individual rods get longer or shorter, but, and this is the key, their combined length never changes. It stays totally constant. That's the proof, right there. No algebra needed.
So we've seen all the components in action. Now let's just take a second to explicitly map the abstract math concepts to the actual physical parts of this model.
And this is it's the beautiful payoff. The abstract idea of an intersecting plane becomes a real angled shelf. The mathematical boundary is now the green ring. Dandelin's clever imaginary spheres are now solid objects. Those mysterious foci are simply the points where the spheres touch down. And that complicated constant distance formula, well, it's just the combined length of these two rods. It literally transforms every piece of the abstract into something real.
You know, what's really amazing is that this design doesn't have to just stay on a computer screen. Thanks to modern tools, we can take this pure mathematical idea and make it physically real.
And here it is, the final 3D printed model. It translates all those theoretical lines and imaginary spheres into a single solid object. You know, models like this really bridge that gap between imagination and observation, making these abstract truths completely undeniable.
It's really an incredible journey when you think about it. From an abstract theory described in a book almost a century ago to a physical object that we can hold and test for ourselves today. It's just a perfect example of how new technology can shed new light on timeless mathematical ideas.
Ultimately, the takeaway here is pretty simple. Abstract geometry really demands imagination, but tactile geometry, it provides proof that you can actually feel. And it makes you wonder, right? What other beautiful equations are just sitting there on a page waiting for someone to finally build them?